How are we doing, guys? We're looking today at Fundamental Applied Maths, Chapter 9b, page 166, 167, questions 2, 5, 8 and 10. Depending on how long this takes, I might do 10 in a separate video. I'll start my timer there. So question 2, this is a continuation of hydrostatics. Says to us, an upright cylindrical tank has height 11 centimeters and diameter 10 centimeters. It's filled with an oil of relative density 0.85. Find in terms of pi and g the pressure at a point on the base, the thrust on the base, and the weight of the oil. Okay, so the relative density is 0.85, which means the density is 850 kilograms per meter cubed. Now, we're in meters cubed here, so we need to work in meters for our distances. Okay, so if our height is 11 centimeters, we'll change that to 0.11 meters. Our diameter is 10 centimeters, the radius that we're always interested in, so that's 0.05 meters for the radius. The pressure at the base is the first thing they've asked us to find. Well, that's using our rho GH formula, which is one that we'll be using a lot in this chapter. So pressure in a liquid is density times acceleration due to gravity times the height of the column of liquid above it. We can just commit that to memory and use that regularly now. So the density here is 850 times g, which will leave us g, times the height is 0.11. So the pressure on the base in terms of pi and g, so in terms of g, is 850 times 0.11 is, 93.5 g. Thrust is essentially, it's a force that acts upwards. You can think of it in this case as being kind of similar to the normal force, okay? That the force acting downwards has to be balanced out by force acting upwards. That's in this case. In general, it's going to be for a body immersed in a liquid. If I had a perfect square as the base of something here, the thrust is a force felt at that point in the liquid. If you find the pressure of the liquid there will be an upward force on the base called thrust, and it's pressure at that point in the liquid multiplied by the area of the body that's acting on. Now, similarly, there'll be a downward force of thrust at the top. It'll be lower because the pressure there is higher. The pressure down here is higher. So this will be a smaller thrust than here. So you'll always find that at deeper points, a body has more thrust acting on it than at higher points on the same body, which means thrust always has a net upwards effect. In this case, anyway, the thrust at the bottom of the liquid, pressure times area, is 93.5 times g times the area is going to be pi r squared, so pi times 0.05 squared, and that's going to be 93.5 multiplied by 0.05 squared, so 0.23375. 23375 pi g. Okay, we're finding answers in terms of pi and g. Find the weight of the oil is the last thing they've asked us. Well, that's the volume of the oil multiplied by its density. Volume here is pi r squared h times the density. So that's going to be pi times 0.05 squared times 0.11 times our density of 850 kg. Volume times density is going to give us the mass. So this is the mass we're finding. The weight then is mass multiplied by g. Okay, so what does that come out as? 0.05 squared times 0.11 times 850 is equal to this number here, and surprise surprise, 0.23375 pi, and then when you say what's the weight, when you multiply that by g, it's 0.23375 pi times g. Okay, so no surprise there that the thrust, no surprise to me. The point they're trying to illustrate is that the thrust at the bottom here is equivalent to the weight acting down. It has to be matched by an upward force, which we call thrust. And it's similar, like I said, in this instance to maybe the normal force if this thing is sitting on a table or something like that. Question 5. Okay, a U-tube. This has nothing to do with the The website contains mercury of relative density 13.6. So this is just a tube like this in this shape here that you put a liquid into, and the liquids will balance themselves out such that the pressure, I suppose, at any point will be the same. So it's a general rule in hydrostatics that if you pick a point in a liquid here and another point at the same depth, that the pressure at those 2 points will be the same. Okay, if you go higher, you get less pressure, lower, you get more pressure, but at the same depth, you've got the same pressure. So that's what these U-tubes work with. It's the fact that at the same depth, you'll have the same pressure. So you've got a dense mercury here, and then you've got less dense water being poured into one side of the tube. 17 centimeter column of water is poured into one branch as shown. Find the difference in the heights reached in the two branches. So we're going to say the pressure right here at the mercury water boundary is the same. Okay, so rho GH equals rho GH is what I'm going to use here. So the pressure from the water is, rho is 1000, G, gravity, and the height is 17. The pressure from the mercury is a much higher density times G times obviously a smaller height. So let's see what that height is. Well, G's cancel. In fact, even the densities more or less cancel. You get left with 1.36, which is the relative density, 13.6, which is the relative density of the mercury, and you get H is, it's 17 divided by 13.6, and 17 over 13.6 is 1.25 centimeters. Now, the question is asked for the difference in heights, so that's the difference from here to here, so that's 17 minus 1.25 is 15.75 centimeters. Second part of that question says a oil of relative density 0.85 is poured into the other side, this side here, until the liquid in each branch reaches the same level. Find the height of the column of oil. Okay, so we're going to pour oil in here until we have, here's our oil, and our density here is, our relative density is 0.85, so that's 850 kilograms per meter cubed. So what we know now is that whatever height the mercury is at, and these will obviously slosh around a little bit, but whatever height the mercury is at, so I'm going to call that in here X mercury, and then Y oil. Okay, so you've got mercury up as far as here, and then sitting on top of that you've got oil. So X plus Y together, if they're now at the same height, which is what the problem said, X plus Y together have to be 17. Okay, the height of the water column. So you've got this other column, a little bit of mercury, a little bit of oil, but together they have to be the same height for this to level up. As well as that, at this point here, we say pressure equals pressure. Okay, so rho GH from the water is not too bad. That's going to be 1000 G, and the height is 17. On the other side, you've got pressure from the mercury and from the oil. So from the oil, you've got rho is 850, G, and the height of oil is what we've called Y. Plus, you've got additionally, at this point here, you've got the pressure from the oil and the pressure from the mercury as well, which is 13600 G times, well, our height of oil we're calling X. Okay, so G's cancel out of that. And we're left with 17,000 equals 850 Y. Now what we're trying to find is the height of the column of oil. We're trying to find Y, so I'm going to substitute for X in just a second. So I'll leave that as 850 Y plus 13600 X, which I'm going to replace with 17 minus Y. Okay, and solving that, I have this done, so I'm just going to, oh, I've lost my page. Excuse me. Solving that is going to give us X equals, Y equals 16.8 centimeters. Okay, so I'll let you do that bit of work yourselves. Question 8 says a cylindrical vessel of diameter 12 centimeters, here it is here, so this radius is 0.06 meters, again working in meters, is partly filled with oil of relative density 0.9. So it's partly filled. Density here is 900 kilograms per meter cubed. Different type of oil to previously. A sphere of diameter 6 centimeters, so radius 3 centimeters, is totally immersed in the oil. Find the increase in the depth, the pressure, the increase in the pressure at a point on the base, and the increase in the thrust on the base in terms of pi. So after we immerse that sphere, the oil level is going to rise. Okay, and if you look at this shape here, what you're looking at is a cylinder of some height h, and that's what we want to find, is the increase in the depth or the increase in that height. So the volume that the oil rises by, or the volume of displaced oil, is the same as the volume of this sphere here. So that cylinder there has the same volume as this sphere here, so we can say 4/3 pi times 0.03 cubed will equal the volume of the cylinder is pi r, our radius, pi times 0.06 squared times the height, which is what we're after. And solving that is going to give you h equals 1 centimeter, 0.01 meters. Again, just I've done that earlier, so I'll just, rather than you watching me work it all out, that's how we got that equation, which solves to 0.01. The next question, find the pressure at a point on the base. Okay, well, pressure is rho GH, so pressure at the base is rho is 900 kilograms per meter cubed. Rho times G times our new height now is 0.01 meters. And that is going to be 9g newtons per meter squared, or 9g pascals is the unit we use for pressure. It's the same as a newton per meter squared. The third part then says the thrust on the base. So thrust, as discussed earlier, is pressure multiplied by the area across which that pressure is acting. So that's 9g, if you remember, that's 9g newtons per meter squared will be equivalent unit, multiplied by, well, how many meters squared is the area at the base of this thing? It's a circle, so it's going to be pi times its radius squared. And that's the increase in pressure is what we're finding. So the increase in thrust. The increase in pressure here came from the increase in height. So that's 9g pi, and do I have this here as well? Question 8. Sorry about this. Yeah, 0.0324 pi g. Thrust is a force, so that's in newtons. Okay, so I'm going to do question 10 in the next video.